So this is the problem that we have, and let's try to break it down and see what it says. How many 5-digit positive integers exist where the digits are not increasing from left to right? So what does this actually mean? It means 5-digit positive integers, and I'm just going to assume that every digit or integer I talk about in the solution is positive, like just not bring negatives at all into the case. Not increasing, I think a better way to phrase this for me would be the digits are either equal or less than the digit that it succeeds because it's left or right. Another way to call this is, I'm going to make up my own term here, is descending but with apostrophes. So it is descending, but the only thing that doesn't make it descending is equal. But what descending means here is that there's a generally downward or equal trend. There's never an upward trend. So we can equate it to descending, and you'll see how that works out in the solution later on. Let's try to get a general case going for this problem. So it's basically saying that if we have 5 digits, and I'm just going to make the variables A, B, C, D, E, that A cannot be 0 because it's 5 digits, and A has to be greater than or equal to B, which has to be greater than or equal to C, which has to be greater than or equal to D, which has to be greater than or equal to E. This is exactly what the problem is saying. So how would you go about solving this? Me, naturally, the first thing I would account to would be casework. But there's several problems with casework in this specific situation. It's very lengthy, it's very error prone, and it's not scalable. And the reason for this is that as A changes, for example, if A is 4, there is a certain amount of set of digits that can be for B to C, because B to E cannot be greater than 4. But when A is 8, B to E can also be up to 8. So that set increases. And how much does that increase by? How much does it decrease by? In order to count all of that is going to be very messy. So unless you want to take an eternity, I would not go to casework. And usually when there is so much messy casework, there's a very key insight to such problems. And let's try to find that instead. So let's imagine that you have a bag. And in that bag, you have digits. So you have the digits. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And forget about this second half of the problem. How would you go about making 5-digit positive integers from this bag? You would take the bag, you would take out a digit, you would note it down as the first digit, you put the digit back in the bag, then you take out another digit, you note it down as second digit, and then you do that 5 times. The key here is that you do the order matters. If you take out a 3 in the first try and then you take out a 3 in the fourth try, that's not the same thing, right? Because those make up 2 different numbers. But the key insight that I want to say is that what if the digits are not ordered? Because we're trying to find a way to devise the properties of this non-increasing 5-digit integer. Instead of ordering the digits, what if I consider them as a set? Here's what I mean. So let's say the digits are 2, 3, 1, 3, 7. Instead of considering them as this number, if I consider them as a set, so set, the digits can be shuffled around as 2, 3, 1, 3, 7. There's always, and this is the key insight, there's always and only one non-increasing 5-digit number. And the reason this is because it has to be in our so-called descending order. The highest digits have to be at the front, and then the lower digits have to follow. 7 has to be first here, because if 7 is not first, then something else has to be first, and then it has to be after that, and then it won't satisfy the conditions of the problem. 7 has to be first. Then it has to be followed by 3s, and then 2s and 1. It has to be this sort of descending order in that sense. If I give another example, right? Now I'm going to consider this a set, not as orders, because we just have to take out 5 digits. If I take 7, 7, 7, pretty unlikely, but we'll go with it, and then 6 and 0. This only has one number that satisfies the condition of this, which is that the 7s are in the front, followed by the 6, and then the 0. Oh, it's in the same order. But it always has, because we can always arrange them in descending order, and it only has one way to arrange that. So this problem equates to saying that you're counting the number of combinations with repetition. I spelled that wrong, but that doesn't matter. You're counting the number of combinations with repetitions. What does this mean? Combinations, because the order which you draw out these numbers in does not matter. It's a set. If I draw these specific numbers out in 3, 2, 1, 3, 7, I switched 3 and 2 here, right? This still corresponds to the same number. Likewise, if I draw some other set arrangement of this set, it still corresponds to this same number. So the combinations, it's not permutations where order matters, it's combination. But it's also combination, the repetition of the digits. There can be multiple times where a digit occurs. So how do we count this? And there's one thing to know, is that there's only one exception. Then the one exception is when there are all 5 zeros. So if I draw 0, 0, 0 5 times, I have to subtract that because that is not possible. But how do we go about counting this? Let's look at an algebraic approach. So if I represent C0 as the number of times 0 appears, C1 as the number of times 1 appears, and all the way until 9. This has to equal 5. And the reason for that is because these are the number of times each digit occurs, and the number of digits is 5 digits, is a 5-digit number, it has to equal to 5. So this problem is the exact same thing as asking how many solutions are there to this equation where each one of C0 to C9 is between 0 and 5. I can map something, right? In here, the 7 appears 3 times. In here, the 6 appears once. And the 0 appears once. And the rest appears 0, right? That's the mapping from this to this. It's the same problem. How do we go about finding that? And the way we go about finding that is we use something called the stars and bars probability method. Here's what I mean. So consider dividers. Dividers that divide this into 10 equal sections of space because there's 10 digits. So there's 9 dividers. I'm going to put each divider at a plus sign. And what this represents is that each space here corresponds to the variable above it. So the number of, and we're going to assign 5 as points. So points as in like 5 points, as in 1 point here, 1 point here, and 3 points here. But there's 5 points. And the number of points in each section corresponds to the value of that variable above. So this corresponds to C0, C1, C2, all the way up till C9. So there's 9 spacers and 9 spacers and 10 different sections with 5 points to each section. So this problem is equivalent to just asking how many ways can we distribute these points into these 10 spacers. In other words, how many ways can we just shuffle these around? There's a total of 14 items here. How many ways can we shuffle these 14 items around to get a specific combination of the number of digits that appear? And we know that if we get a specific combination of the number that digits appear, there's only one number that forms which satisfies this condition. And the way to do that is to note that there are 14 items here, and those 14 items can be represented by 14 factorial because there's 14 spaces. So the first space can have 14 items, second space 13 items, so forth. But you have to divide that by the number of repeating items. These separators and these points, they're indistinguishable, meaning that they can be switched around. So because it's not the separators that mark the variables itself, it's a space between the separators that mark the variables. The space from nothing to the first separator is always the number of zeros. The space from the first separator to the second is always the number of ones, and so forth. So there's a total of 9 separators. So that's 9 factorial because you have to divide by that. And you have to divide by the number of stars there are because they're indistinguishable. And that's 5. So this is the same as 14 choose 5 by definition, which is when you calculate it, turns out to be 2002. And remember how we said that there is -1 here because of the case when all these 5 dots are right here, because when it's all zeros, that's not possible. This gives us the final answer of 2001. And there you go.